So again, welcome to our FusionEPtalks, our students webinar. So first, let me introduce our speaker today. Our speaker is Pedro Molina Cabrera, and currently he now is in postdoc at PSFC-MIT on this academic on Max Planck Institute for Plasma Physics in Garching in Germany. He studied physics of turbulence through the diagnostics and some moderation efforts in the ASDEX-Upgrade, and did his PhD in the Swiss Plasma Center in Lucerne. He also was a batch of the FusionEP network and was there in Madrid and Nancy, graduating 2014. And before that, he undergraduated in Canada. And this talk right now will, as the title already suggests, go about isotopics. And without giving too much information, I will hand over to Pedro. Talk you through this.
Okay, thanks for that introduction, Tobias. Hello, everyone. It's a pleasure to be here. Thanks for the invitation. Yes, let's take it away. So I wanted to give you just a kind of an introduction to this thing that at least, well, if you work a bit on transport or in validation and turbulence in general in tokamaks, you will sometimes maybe hear this word, the isotope effect, this term, and there's a lot of mysticism and mystery around it, and I wanted to kind of explain where that comes from and show you at the same time what I'm working on right now. There's this postdoc here at ASDEX. So how does tokamak turbulence and transport changes with ion mass, essentially? Right, so just a quick outline of the talk there. After an introduction, I'll go through not necessarily deriving things, but some results of general laboratory plasma transport, moving towards the tokamak. Then I'll show you these measurements that I've done on ASDEX of local fluctuations of electron temperature with these diagnostic, the correlation ECE. And then I'll conclude and kind of pose some questions for the future, because this is really not solved, by the way, the isotope effect, as you will learn. So there's some similarities between the plasma and a thermos, which we are all familiar with, both, hopefully. They're a bit different beasts in that turns out that the density of particles, I guess in this case, water molecules, is much higher in a thermos. And if you have a good thermos, you can keep your drinks warm for about an hour or so. In the tokamak or in any magnetic fusion device that actually reaches burning conditions, you would have something like less density in particles, a lot less. So plasma in that case, but of course the temperature would be a lot higher, hundreds of millions of degrees, and the confinement time of the energy in this case, the energy confinement time is about 1 second for when you reach the conditions of ignition. And so they're both trying to keep things hot, essentially. The thermos, keeps your drinks hot, and it's very good at doing that. The tokamak is trying to hold on to this dense hot plasma for as much as it can, and they're similar in that sense. Just a quick heads up, because later on it's funny that this is going to become there's going to be an interesting parallel between a thermos and the tokamak. But just to give you, of course, you know, perhaps you know already, obviously, how this thermos works, but I personally didn't know the details of it. But essentially, it's a flask, and as you see, there's of course you put your hot coffee or tea there, and you have this in the inside. There's this wall that is silver surface, so that if you have any radiation kind of coming from the hot fluid, it will bounce inside and kind of be maintained, so you won't absorb radiation on the wall. And there is a layer of vacuum between this hot coffee and this hot inner wall here and the outer wall, and that's really the secret of a thermos. Initially, it was called a vacuum flask, a Dewar after its inventor. So it is really here. So the equation, for example, the physics, if you were to say, okay, how long would my tea or my coffee stay hot? Like the equations of heat transport in the hot coffee are very simple. And it's interesting because it's in this vacuum where where you have this discontinuity, as I kind of sketched it here roughly, but so the outside temperature first can be very, very low, or in the case of a day where it can be very hot compared to the inside. But the fact of the matter is that you have this jump in temperature essentially because your heat conductivity goes very, very, very low due to the vacuum that you create. Of course, there's no perfect vacuum, and of course there is this insulated supports that you have some heat transfer here. It's not perfect, but it is the vacuum that keeps the things hot, that isolates the conductivity of the heat conductivity in this diffusivity equation, which I'm hoping you're familiar with, is what really is dropping to almost zero in this vacuum region. This is just a definition of the confinement time, because I might be using this in the future. It's kind of like the ability of the bottle to hold on to the energy in this case. And the energy in the case of a tokamak is an integral of the pressure inside the machine. So the energy confinement time is a measure of how long can you hold on to a certain amount of energy. If you were to shut down all your sources of power, you would get a decrease, an exponential decrease in the energy stored, and this is this energy confinement time, which is kind of like a 1/E decaying exponential length. Good thermos, in the case of your tea or whatnot, should have an infinite confinement time, perfectly speaking. And of course, we want to have a confinement time in our tokamaks also to be the largest possible. So I'm saying all this because you can think of the physics of the thermos. And can you find, for example, you can ask this question: can you find this chi, this heat diffusivity constant for a tokamak? Like how do you calculate that? Like, could you, if you knew how to calculate it, it'd be great, because then you could just design the machine and predict what it would do, and you can say, okay, if I build it this size, then it would work for sure, for example. So it's very important to answer this question. And what the isotope effect problem relates to is trying to calculate this chi, but for different ions, because most tokamaks today, like ASDEX, where I work in, TCB, where I did my PhD, and I think D3D, for example, are all working deuterium. So we have a lot of experience with deuterium. JET is an example of a machine that can run in tritium, but it's quite rare to run in tritium. So most of the experience is in the deuterium plasmas. And but fusion, of course, we know will happen with a mixture of deuterium and tritium. So we need to know how this chi changes between hydrogen, deuterium, and tritium. So stay tuned until the end, so that you would see what happens with this chi, or with this heat, this confinement time. And just like we can ask the question, would the thermos hold on to the coffee or the tea better? Does the tokamak hold on better to or keep the plasma hotter if the plasma is hydrogen, or if it's deuterium, or is it tritium? So it's an interesting question to pose. And so I'll go through first a few simple equations, just to give you a sense of the dependencies of things, like how can we calculate these diffusivity constants. And my goal here is to introduce you to the concept of Bohm diffusion, which is something that you can find in textbooks, but that I think it's important to introduce, because later on I need to go back to this definition of Bohm diffusion. So if you take, for example, the simplest plasma, something you just put some electrodes and put some kilovolts, you put some vacuum, some gas in a very low pressure discharge, you would have a non-magnetized, highly collisional, not fully ionized plasma. So this is the most simple laboratory plasmas, like the Passion tube, for example. In there, what you have is transport that you can model as a diffusive process, like Brownell motion. Essentially, you can model this diffusion as depending on a step size and in a collision frequency, or the average time between collisions. So the average size of a collision and the average time it takes to make this collision. So you can calculate, for example, a diffusion. You can calculate the amount of particles that are escaping your plasma like this. In the case of a unmagnetized collisional plasma, this this diffusion constant, as you see here, is strongly dependent on the collision frequency, and this collision frequency is the collisions between your plasma species, so either your electrons or your ions, and neutral particles. And in that case, for example, if you had something like, in that case, if you assume a given probability and you integrate over the velocity of your plasma, for example, assuming it's a Maxwellian, you can get a dependence of this collision as a function of 1 over the square root of the mass. So if you have a heavier ion, essentially it's less likely that you would have this collision. So the diffusion constant, so a tritium ion, in that case, a heavier ion is better confined than a lighter hydrogen. In the case of colliding with other particles, you can think of it as a bigger I don't know, ion having a harder time escaping due to a more higher likelihood of collisions, because it's just bigger essentially. Now, the next step of complexity is when you have a magnetized plasma, and you still have collisions with neutral particles. So I still call it collisional, in that it's collision. What I mean with collision is like with neutral particles. So in that case, the diffusion essentially parallel to the magnetic field is the same. You still have collisions with particles, neutral particles along the magnetic field lines, but perpendicular to the magnetic field lines, you reduce the diffusion. And this is something that we all intuitively understand. Perhaps by turning on a magnetic field, we're all told you confine the plasma. And this translates into having the diffusion perpendicular to the magnetic field being reduced by the presence of this magnetic field. So that's what this constant here shows and whatnot. And if we then try to look at the dependencies again of sort of an equivalent step size and collision frequency, we get that this step size now becomes the ion Larmor radius. So essentially, you have particles that are gyrating around the magnetic field lines, and suddenly they find some neutral particle, and then they collide and they kind of move a little bit further out, for example. But then their step size is this ion Larmor radius between collisions, essentially, as you can see in this sketch here. So that's interesting, but what's interesting because of that is that then the diffusion constant is now directly proportional to the ion mass. So if you have an ion like tritium, like a heavier ion that kind of just makes a larger ion Larmor radius, then this particle will diffuse faster in the magnetic field. So that's interesting how it goes from perpendicular to the field, it will diffuse faster. So that it's interesting how you could get a reversal already of the mass dependency on the diffusion. Now, what we have in reality, and it's not even the beginning of the story, but you can, make a calculation of what happens in a fully ionized plasma. So if you go to the conditions of the Tokamak that I showed in the beginning, you have a relatively dense plasma. You also have actually a very hot plasma. So when you reach these temperatures, the amount of ionization is negligible. So you have now, instead of diffusion due to colliding with neutral particles in the core of a plasma, you don't have any neutral particles. It's so hot that it's just plasma everywhere. And the collisions then become different now, except for the scraper layer, which is at the very end, the edge of the plasma. So now the diffusion, if you want to think of, if you assume, of course, that the picture of diffusion is correct, if you say, let's go with diffusion, you now have diffusion due to Coulomb collisions. And you might have studied this in your courses. What this means is essentially collisions between charged particles, and essentially the patterns, the trajectories of the charged particles get affected by the essentially Coulomb interaction between charged particles. And so then if you derive this collision operators, and it's a long calculation, but you end up with something you can also express like a diffusion constant perpendicular to the magnetic field, which is what we're interested on, which now has very different dependencies. So now you see a dependency on the temperature, and actually because this guy here is the resistivity is to the temperature 3/2, you actually have a dependency of T to the -1/2. So a hotter plasma, as you increase the temperature, you get less of a diffusion, so less collisions. And you have now a dependency with density. So the more dense your plasma, of course, more collisions you're going to have, more Coulomb collisions. So you're going to diffuse faster if you have a denser plasma. And then you also see here a dependency of the magnetic field square, which is good news for fusion or for magnetized magnetic confinement fusion, because higher fields should lead to less diffusion. Now, of course, unfortunately, it's not that easy. This equation here, this classical diffusion constant, actually doesn't work in reality so well already in the laboratory plasmas, and there were many reasons for this. It could have been, things like problems with the magnetic field homogeneity and waves, as we'll see later. Instabilities can be a problem. But what happened is that these guys in 1946, they were studying how to remove uranium isotopes with high power magnetized arc reactors. Essentially, arcs, very high power plasmas. So they tried to understand what the diffusion perpendicular to the magnetic field would be, and they came up with an empirical calculation. They said, it looks like our data fits this. It's directly proportional to the temperature, which is nice. We saw that before. Actually, it's the inverse. It's not even the same dependency on temperature. There is no density dependence, and the magnetic field dependence is over 1/b only. So that was, it fit the data essentially. This Bohm diffusion. So this is that is the Bohm diffusion equation. Or the form of the diffusion coefficient. And again, this 116 is completely random, and it's what this leads to in terms of the particle confinement, for example, here is something in direct proportion to the magnetic field, and not squared, and no density, and no and something about the size of the machine, but it's not and in direct proportion to the temperature. So in that case, actually, it's funny. We had a mass dependence here above on the diffusion constant, which was the mass to the square root. So, for example, in that case, again, a heavier ion would diffuse faster, because it would have essentially more a higher likelihood of colliding. And so in the case of the Bohm diffusion, which turned out to fit the experiment very well, you lose this dependence on the mass. So according to the Bohm diffusion, if you have hydrogen, deuterium, tritium, boron, any kind of plasma, it should give the same diffusion. And it's amazing that it worked over a range of scales that was quite surprising. And it's quite fantastic actually that it worked. And again, as I said, and the bad news also is that it's a lot essentially larger than the classical diffusion by a factor of 10,000. So the Bohm diffusion let the particles escape much faster than the classical was expecting. So this is what you find already in these classical plasmas, and they were able to explain it due to problems in the magnetic fields shapes that they had, and some of them were also due to drift waves, which is something that we'll see in tokamaks is also the case. So what happens in a tokamak? A tokamak is a fully ionized plasma. It's a very hot plasma. And in addition to that, it's in the toroidal geometry. So, so you have, you can also derive equations for the classical Coulomb collisions. But in the case of a tokamak, you have to incorporate the fact that you have a toroidal geometry, and what that does to these collisional operators is introduce trap particles, and these are essentially particles that near the edge of the plasma, instead of having a normal trajectory around the magnetic field line, they kind of bounce back and forth. And the projection of this bouncing back and forth in the polar plane looks like a banana. That's why they call it the banana orbits. And you can see that depending on the energy of these trap particles, they can have weird elongated bananas and so on. So essentially, in simple terms, what the tokamak geometry adds is the complexity of the classical collisions plus these trap particles, which leads to some factor in front of the classical collision coefficient that makes it larger. So you get more diffusion due to these trap particles. But essentially, you maintain this neoclassical, classical diffusion mass scaling, which is to the 1/2. But then if you go to the experiment like it was before, not as bad as it was before, you get an increase of a factor of 200 over this neoclassical transport. So you still don't recover the transport that you, if you think of classical formulas, don't recover the real transport in a tokamak. Sometimes though, when there are things like ion transport barriers, or in the H-mode pedestal, for example, for ions, the ion diffusion can be very close to the neoclassical. So in terms of fusion research, the neoclassical estimate is kind of the best that you could possibly do, essentially. But and again, in this case, the dependency with the classical diffusion is still there with the square root of the mass. What actually is happening in a tokamak is that in addition to these collisions, classical collisions, you have micro instabilities, which interact nonlinearly to produce something that people say plasma turbulence. Now, this is broadly accepted to be the source of anomalous transport. So the fact that the transport is larger than the classical neoclassical estimates in the past used to be called anomalous transport. Now it's more sort of accepted to be due to plasma turbulence. And this turbulence is the result of the nonlinear mixing of various types of waves, essentially drift waves that exist in the plasma. I'm here just showing a sketch on going the details of each individual drift wave. But mostly here I'm showing the ITG, total ITG sketch of the picture of how it comes to be. Essentially, you have perturbations in the density and potential, and due to if you have a strong perturbance in the density, you already get a bit of an electric field, and this electric field with the magnetic field that you have in the tokamak creates a convection, a convective cell of sorts that pulls the plasma outside, it pushes the plasma out. So you get this kind of convection cells wobbling and pushing the plasma out. And these instabilities use the energy in the profile gradients. I really like this picture from Pablo Rodriguez Fernandez thesis, where he kind of explains the paradigm, so to speak, of drift wave turbulence as we understand it right now. So we have external heating, and you know, we have all these magnets turned on, and we have the current, or ECRH or ICRH or NBI, and we have all kinds of power heating the plasma, which creates these gradients, which is what you would like to have. So you want to have a hot core, and you don't want to burn the walls, so you naturally have a gradient. But then in nature, just by the fact that there's very strong gradients, you're going to have turbulence is kind of like a natural way to get rid of this heat as efficiently as possible in many different scales, so these gradients give rise to these drift wave instabilities that I showed before, the example of the ITG, and you have a very complicated physics of various drift wave instabilities interacting with one another with a nonlinear mixing of their growth rates and so on, and different saturation mechanisms. You have also sonal flows, radially localized, essentially flows that regulate these nonlinear saturation, and you end up with something. Turbulence is the word for chaos, like very chaotic, lots of different scales, and essentially convection in all kinds of sizes and all kinds of frequencies. So it's not localized in frequency, it doesn't have one size, it has lots of sizes and a broadband spectrum. And this leads to the turbulent transport, or the transport that is larger than the neoclassical transport. And then this has an effect on the gradients, and this has an effect on the drift wave instability. So you have kind of a loop there that kind of exists. And so this paradigm is quite complicated to understand and to model. How do we calculate these diffusion constants in plasmas? So nowadays, the most advanced, or sort of what is considered to be the most sophisticated model, is to solve the Blasso-Maxwell equations, which is the most basic plasma equation that you can have in 6 dimensions. I won't go to the derivation of this, but essentially a gyrokinetic code takes this very complicated equation and simplifies it only by taking electrons and ions to follow, to gyrate around a magnetic field. So you simplify this equation into 5D, and you try to solve it. So it's a very, very difficult task. It's highly nonlinear, and there are specific analytic solutions to this equation in very specific conditions, but not in general. And that's why we use, to solve this equation, gyrokinetic codes. And you've heard this word gyrokinetic externally. The problem with these codes currently, and I think for a while, is that they're heavy to run. They take thousands of CP hours to run one location even. So it's quite hard to get to the pictures that you see here on the right hand side. It takes a long time to run. But they are really the most advanced techniques that we have to compute these transport coefficients, to understand the turbulence. And they have been able to reproduce the heat fluxes and even some of the turbulence properties in the core of the plasma. Not in 100% of all the cases, and we're still working on that. Like, part of my work is validating these type of codes. And here on the right hand side, you see this gyro code and output. So you see all the various types of the convective cells that I was talking about, and the different sizes of turbulence. Right. So you can calculate it this way. You can use this machinery, these complex codes, and you can really get to the bottom of the problem. But even that is a bit complicated because we're not quite sure that the equation is being solved perfectly, and we're still validating that. And this takes forever to calculate. So how else do you do this? How else can you calculate this chi, or this diffusion constant? How did they even do that in the 90s when they had to decide, ITER, okay, it's in France, and then how big is it going to be, stuff like this? Like, they had to come up with something. And for these people, use this thing called scaling laws. And I'm not personally a huge fan of these things because they're essentially they're empirical. They're an attempt of the community to do something like the Bohm diffusion, which was so fantastically successful. And they work actually as you can see here on the right hand side. It kind of fits most of the tokamaks, but it is a rough thing to do to try to multiply all of these sort of engineering parameters from the outside. So you have the plasma current, the plasma size, the density, and you just assign an exponential to a value to each of a power estimate to each of these different engineering quantities, and you draw a line essentially. I think these approaches would definitely work well if you're trying to interpolate things. So between experiments that are, so say you have a really big machine and a very small machine, and you're trying to say what's going to be like the behavior at a mid-sized machine, this would be an acceptable approach. The problem is when you try to extrapolate, because you assume that the same transport processes are taking place, and this is an issue. But as you can see here, nonetheless, that there is a mass dependence again. So you see that it seems like, and I will explain later this in more detail, but there is a positive ion dependence, which is good news for fusion. So you expect a better confined plasma for the deuterium-tritium than you would just for the deuterium, for example, or for hydrogen. But I wanted to say that there's almost no physics in this approach, and it's a rough approximation. Another way to go around this idea of, okay, I don't want to run these super complicated codes. It looks like just multiplying constants from the engineering side may not be the best way to do it. Another approach, kind of meets between the two, is to look at non-dimensional quantities. So these are essentially quantities like the plasma beta, the collisionality, the size of the IMO-Lambda radius, and you essentially make them non-dimensional. So you scale them by some constants, so they don't have a unit. Essentially, is what it means, non-dimensional. And you for example look at gradients, and you multiply the gradient by, or divide by the temperature times the radius, for example, to give you something non-dimensional. And the interesting thing here is that you're kind of using some fundamental plasma parameters. How likely are collisions to be the case? What's the ratio between the pressure of the plasma and the magnetic field pressure? What is the ratio between the size of your ion Lambda radius versus the size of your machine? So if your machine is huge or your machine is small, this would change these parameters, this rho star. So that's the approach of non-dimensional scaling. And so if you were to say, okay, let's say that the plasma has a gyro-Bohm, a Bohm-like scaling. So you essentially you say, okay, the heat diffusivity or the particle diffusivity scales like the Bohm case, temperature over magnetic field. And then what I would like to explain you now is this word gyro-Bohm, which you would hear a lot in the world of isotope effect studies. Is like essentially you take the Bohm scaling, and in addition to the Bohm scaling, you multiply by the rho star, this constant that I showed before, which is the ion Larmor radius divided by the size of the machine. Now, the inclusion of this constant kind of gives you an idea on the turbulence size of your eddies or your turbulence. So you could conceive it this way, in a physics way, or to give you sort of a picture of things. So if this exponent here was 0, essentially you expect the turbulence size to be about the size of the machine. So these waves, essentially the size of the characteristic size of your turbulence is as big as your machine. This would be like Bohm diffusion, because Bohm diffusion doesn't care about the ion mass or the ion Larmor radius. It cares just about the temperature and the magnetic field. And as we saw before, I showed you the particle confinement time. It depends on the size of the machine, the radius. If this exponent was to be 1, then the turbulence, you assume it's about the size of your ion Larmor radius. And if this exponent is -1, so it's like indirectly proportional, then the turbulence will be much larger than the machine. And so you have things like ELMS, for example, or stochastic reconnection processes could have a kind of a diffusion in these scales. So something when the magnetic fields really kind of disappear and you have much larger transport. So, and then you make this assumption and you ask yourself, well, which scaling does the plasma give me? Like what do I see in the experiments? So this is just to give you an idea. If you had, I won't read the specific details of how people came up with these numbers, and we can talk about it later. But if the turbulence really was gyro-Bohm, so it's about the size of the ion Larmor radius, to get, for example, ignition in ITER, you can make the estimate that you would need 80 megawatts. But if it was Bohm, you would need 600 megawatts. So that's a lot of power. There's of course uncertainty here, but it's an important question to answer to have an idea. What is interesting is that the theory, if you take the gyrokinetic equation that I showed here, and you solve it for ions, assuming adiabatic electrons, so a very simple like limit of that equation approximation, you recover a gyro-Bohm scaling. So you assuming that the turbulence has the size of the ion Larmor radius. So it's interesting that theories, simple gyrokinetic codes, and even in the core of modern day tokamaks, you still get a gyro-Bohm scaling. So the theory likes the gyro-Bohm. It's consistent with simple theory, the gyro-Bohm scaling. Now, what we can do, or people like experimentalists like myself, what we can do is actually go and measure what does the turbulence look like? Like, is it Bohm? Is it as big as the machine size? We cannot see the turbulence. Is it like the ion Larmor radius? And so that's what I did in ASDEX. ASDEX is ASDEX-Upgrade is a moderate magnetic field machine, very high actually magnetic field, but not as high as other machines, but it's a pretty high magnetic field machine. You can run lots of big currents with it, and it's quite a large machine relatively. It's called a medium-sized tokamak, but I think it's in the large size of things. Has a lot of external power, tungsten walls, and just to give you an idea of the machine, it's a very active tokamak. It's really a privilege to be working here. I can measure. I can create a plasma in this tokamak in ASDEX, an L-mode plasma to keep things simple. And what I'm going to do is try to measure the turbulence properties, and how I do that is with this diagnostic correlation ECE. I don't want to spend too much time essentially explaining the details of the technique, but I would like to tell you just roughly what it's like. Essentially, you're measuring. So when electrons are gyrating around the magnetic field of the tokamak, which is very strong, you get natural emission of radio waves because you have a charge being accelerator. And this is what's called electron cyclotron emission. And it's actually a very useful type of emission. It's the only black body emission from the plasma. So that means that when you when you have when you see this radiation is direct proportional to the temperature that what you see. So essentially, it's like looking at an oven, like a black body, looking at an oven, and you can, by looking at the wavelength, you can know how hot it is, right? And it's the same for a tokamak plasma. Looking at the ECE radiation, electron cyclotron emission, you can see that you can measure the temperature. And what we do in our group is to have these very closely spaced channels of this ECE diagnostic. And because of the specificities of the technique, and I won't necessarily explain you why this is the case, but you have to kind of believe me that if you just have one channel, you would measure a lot of random noise, because the electrons are kind of emitting in a lot of phases, so you get all kinds of interference, and so it's not the signal itself. If you just measure one channel, you will get a lot of background. It's called many names, Nyquist thermal noise, but black body noise. And it turns out that this noise, it's a bit too big to try to measure the turbulence noise, which is in the order of 1% or so. So we used a thing called correlation. So we take two very, very close spaced channels that are not quite at the same place, but we kind of just measure the signals from two very close spaced locations for a very long time, and then we kind of average the background random noise, and we get much lower fluctuation levels naturally, and then we can really access the turbulence, which is really cool. So we can measure the background turbulence with like that. This is in particular called spectral decorrelation techniques. You can access both the fluctuation level by looking at, how does this correlation compare over the radius, for example, but you can also get a radial correlation length, so you can have an estimate of the size of the turbulence as well, which is nice. Here's a look at the plasma that I was doing. Is just a simple L mode with some 0.6 megawatts of ECRH. Here you can see how I repeated this shot in deuterium and hydrogen to study how what's the mass dependence of the turbulence, essentially. I mean, the question that I've been asking all along in this presentation. I was doing density control, and we have a decently matched ECRH. Here's what the turbulence looks like, and you see essentially over the radius you see an increase in the fluctuation level in deuterium and hydrogen. So hydrogen is the blue line here. You see that the diagnostic shows that there's a background rotation of the turbulence a bit higher in deuterium than in hydrogen, and we've seen this also in another diagnostic called Doppler reflectometry. And so it's interesting that the diagnostic shows us this difference in speed as well of the turbulence, the polar rotation. And we see an increase over the radius. If we integrate under the curve these fluctuations, we get essentially a fluctuation level, which is in the order of 1-2% essentially. One of the things that was clear, obviously, is that the fluctuations in deuterium are larger than in hydrogen. And one interesting thing that we tried, which is fascinating, was to take the ratio between the fluctuations in hydrogen or deuterium over hydrogen, so divide the two fluctuations. And we get that ratio to be very close to the ratio of the ion Larmor radiuses. So there is clearly a scaling of the fluctuation amplitude over the ion Larmor radius. So that's great. There's some indication here of gyro-Bohm, because then the turbulence fluctuation level seems to scale with the ion Larmor radius. I did something like I took the same data, the same shots, and I did correlation length studies, and we calculated this correlation length over the radius in the core again, as you see there, and we see that the turbulence is about 5 the size, or the average size of the turbulence. So essentially, if you fit a Gaussian to the amount of correlation between channels, like here, as you see there, you correlate this channel with that one and that one and that one and that one, and you get a kind of a Gaussian, and you calculate a full width half max, and you get a correlation length. And it turned out to be higher in deuterium than in hydrogen, just like we saw in the fluctuation level. And if we divide it over the specific ion Larmor radius, you get them all to line up on top of one another to be around 4.5 to 5 times the ion Larmor radius, which is again independent of the mass and consistent with this gyro-Bohm scale. Which is great, because the turbulence properties of the temperature fluctuations which enter into the, of course, the heat transport, they scale like gyro-Bohm. This is a quick comparison with the gyrokinetic simulation gene, which is one of the most advanced gyrokinetic codes that people use a lot here at ASDEX. And we've compared. We don't have a perfect. Well, we have a pretty good match actually for what we're seeing, and but I'm still on the process of bearing various input parameters to the code to make sure that this is not a good luck kind of agreement. So this is still work in progress, but it's encouraging. We have very good agreement with some gyrokinetic calculations to see what the code is saying the temperature fluctuations should look like is similar to what we see in the experiment, and we're using synthetic diagnostics, and yeah, so it's exciting that the code is predicting similar temperature fluctuation levels. This has also been observed in other machines, just to let you know, in density fluctuations at E3D. So you see a similar scaling of both the fluctuation level and the correlation lengths. And so it is present in density fluctuations and temperature fluctuations. We don't know about potential fluctuations. This is the other thing we cannot measure in the core of a tokamak. But so essentially what I've seen is that the fluctuation level ratio is really very close to the ion Larmor radius, and this radial correlation length again is a constant times the ion Larmor radius. So it would be consistent with gyro-Bohm prediction. But of course, the problem is that the gyro-Bohm prediction would predict that the confinement time is indirectly proportional to the ion mass. So a higher fluctuation level, this is so obviously the case. So more fluctuations in a larger size of the diffusion should lead to more heat exhaust. It should lead to worse confinement, obviously. So the higher your ion mass, you should have worse confinement. And this is this is the picture in the gyro-Bohm scaling. And this is the isotope effect. I get kind of a long presentation to tell you what is the isotope effect. It's this fact. Oh my gosh! Like I measured the turbulence, and it is gyro-Bohm scaling. It obeys the gyro-Bohm scaling. Simple gyrokinetic theory predicts it's also gyro-Bohm, but in reality, the confinement time, the global confinement time, this is the important aspect that you should, if anything, take away from my talk, is that a global parameter like the confinement time does not necessarily have to obey local measurements. So in tokamaks, as we saw before, actually, if you paid attention to this scaling law, we see a positive dependence here on a positive spawning on the ion mass. So it is. This is the isotope effect. The fact that the experiments show better confinement in deuterium, and I'm not complaining. I'm just, this is actually good news for fusion. This is good that the experiments show that you have better confinement in deuterium over hydrogen. This would mean that deuterium-tritium should have better confinement still. So this is good news. I'm all happy. It's just that it doesn't agree with my local measurements of turbulence in an Helmholtz plasma and ASDEX, and it also doesn't agree with the simple limits to the gyrokinetic equation. And so there are a lot of people that have gone on this subject trying to understand what is going on. People have said son of flows, that like so these flows to try to. I won't explain the details of this, but essentially you have various things that can depend on the ion mass that can contribute to this isotope effect. The one that I'm currently most interested in studying myself is effects in the edge of the plasma. So as you go further out than what I did, because remember I measured here about 0.7, 0.6 to 0.8. So once you go out here from 0.8 to 1.0, there some theoreticians have started to say that you have more a specific type of electron turbulence where the electron mass is important, and then if you have the electrons colliding with hydrogen, it's different if you have these electrons colliding with deuterium. So it looks like also electromagnetic fluctuations can be important in the edge. And this is still a field of active research. This is a paper from that just came out from eValley in D3D, showing that in this particular type of LMO they had there in D3D, you see a reversal of the gyro-Bohm scaling. So you see more transporting hydrogen over deuterium in the edge. So it would be almost like I don't want to say, of course, if you put tea or coffee in a thermos, the thermos vacuum behaves the same for the tea and the coffee. But you know what happens in a tokamak is as you go towards the edge, that vacuum of sorts in the tokamak, you get more transporting hydrogen. This is the picture that people are throwing out there. And like this week, I did experiments only in deuterium to measure the fluctuations in that region, in the outside region, to see if I can then compare it with hydrogen and see if I experimentally see this reversal of the gyro-Bohm scale. Because I have seen a very good gyro-Bohm in here. And the theoreticians also expect that the core should be gyro-Bohm. And it's just when you go into the edge, you can have this reversal, and that's where things getting exciting, and that's where we're going essentially. And yeah, so I wanted to just thank you for your attention again. Just keep in mind as a summary that we're dealing with complicated, it's very complicated to model this plasma. You have a fully ionized magnetized plasma in a toroidal geometry. You have nonlinear interaction of various drift waves that lead to transport, and the transport in the edge region is still not super well understood. Again, these are just theoretical expectations. There is still no measurements of the fluctuations in the edge. I'm just starting to do them myself, for example. So this is quite an exciting field, and great progress having achieved with gyrokinetic simulations. I think in the past, now we understand anomalous transport to be due to these drift waves. It's generally accepted to be the case. They can reproduce various things, but we're still validating these codes, especially in the edge. We're not quite sure things go exactly like the gyrokinetic codes are predicting. The isotope effect is a puzzling thing. It's strange for people like me who measure gyro-Bohm scaling to have the isotope effect. So it's strange, but it's good news for fusion, because deuterium-tritium machines will perform with a better energy confinement for free, essentially. for once, we're lucky that we're using heavier ions. So it will lead to better performance in the tokamak. And so again, the picture of the thermos to take away the edge, it can be interesting. Thank you for your attention.
Thank you very much, Pedro, for your talk. Pedro, did I understand correctly that you measure with your diagnostics, you have like these two separate channels, and then you try to average them to get a clear signal, right?
Mm-hmm.
And you said you did it on a long term, like long time, but I didn't understand how this, if you average this for a long time, how you're able to measure these turbulences if they're really happening pretty quickly. Or did I misunderstood something there? You measure with your diagnostics, you have like these.
Yeah, this is a hard thing to explain. Of course, I did not spend enough time on that. I was more on the physics, but I'm very happy to explain. So essentially, so a radiometer normally say you're sampling this thing at a megahertz or something, like you're sampling very fast anyway. And so you measure the voltage that is directly proportional to the power that you measure in the channel, and you have a bandwidth of your acquisition in the megahertz level. So it's very fast if you take and we don't expect most people that have in the past measured the drift wave turbulence, they have found it to be 200, 300 kilohertz or something, like the curve that I showed here. So it's enough. I mean, there should be a lot of stuff out in the megahertz. In my thesis, I found some modes in the edge of TCV, resistive ballooning modes that could, in the presence of an E cross V shear, rotate like mad, and it'd be like 1.5 megahertz. That's very rare. So assuming that the turbulence that you're trying to measure is 200, you're already sampling very fast. And so if you just sample that and you took the FFT of that, it would be white noise, mostly dominated by white noise because of the bandwidths of your signal. And I don't think I can fully explain why that natural noise is there, other than it's a lot of electrons kind of contributing to a noisy signal. And then this is actually correlation is an old technique to get rid of noise that is not common to two systems. It actually comes from astrophysics when you're trying to look at radio sources from two different telescopes and aiming at the same place. But in this case, you're sitting in two locations that are very, very close to each other, not touching one another, but inside one of the turbulent scales. So essentially the turbulence is the same, but the random background noise of the electrons is not the same. So if you take those signals and you do what is called a cross power spectral density, so you take an out power spectrum, essentially an FFT, but not of the channel with itself, but the two channels separately. If you do that only for a microsecond, the problem is that you're going to get a lot of noise anyway, not fully decorrelated in a sense. Like you need some amount of time, something in the order of half a second or something. This is unfortunate for the technique because we cannot see exactly what happens with temperature fluctuation during an ALM or something, for example. It's too fast. Like we need something calm and steady to be able to have enough statistics to get rid of that background noise. That's why, but we're sampling very fast, both channels very fast. And we're not taking an average per se, we're taking an average signal that is common to both over a period of time, but it's not a mean. It's a cross power spectral density. Mm-hmm. Yeah.
Okay, I think I got it. But so it's crucial that the sensors are like in the same order of magnitude of distance as the actually turbulence, right?
Yeah, so, because otherwise you could have just very different turbulence and you might not
exactly. Yeah.
See, yeah. Mm-hmm.
Oh, cool. Thank you.
Hello, can you hear me?
Yeah.
Okay, thank you very much for the presentation. It was directly related to what I'm doing in my PhD right now, which is transport code modeling of the edge plasma.
Oh, nice.
And what actually is the perpendicular diffusion coefficient is a good question for me. So I wanted to ask about a few things. The first one is you have used heat diffusivity, particle diffusivity, and energy confinement time in a very similar setting. Like when you were talking about the classical, neoclassical diffusion, you are talking about the particle diffusion, but in the experiment, you were measuring the temperature fluctuations, which has to do with the heat diffusion. So I would like to ask if there is a relationship between heat and particle diffusion, and whether, like, I can see that they should both somehow relate to the energy confinement time, but is there like any actual rigorous proof that the greater diffusion you have in the core in particular, the greater the slower your confinement time is?
Right. Excellent question. The problem is that like what you're asking for is essentially there is yeah, so I cannot quickly find it, but I could certainly send you. There's this Horton review paper in 1999 where he's actually kind of like the first theoretician to suggest drift waves as the reason for anomalous transport. And while the questions that he has cannot be immediately and they're just linear approximations. They cannot be necessarily applied to all cases in a Tokamak because you have the nonlinear mixing. What you have from simple drift wave turbulence theory is that the particle diffusion depends on the essentially the cross. Actually, okay, I know exactly the paper where that's at, and I can show you now. Sorry. I was looking for a presentation of mine, and now I realized that this is in this paper that I can pull in 2 seconds here. This equation is exactly your answer here. So the particle diffusion of linear, which is in the very core, I think it's not too different from reality. The particle diffusion is essentially a function of this, I guess, ensemble average of the density fluctuations and the potential fluctuations, or the electric field in this equation here. So there, the angle, the cross-phase angle between the density and the potential fluctuations is important. Because if this is, for example, 0 degrees, it would just go right through. If it's 90 degrees, if they're perfectly out of phase, then you should have like no particle diffusion. And in the case of heat diffusion, that's where the temperature fluctuations come in. It's exactly as you said. And then there's also a sort of a term for the density fluctuations. Yes, I showed you only data like this, like the temperature fluctuation data, which enters into this equation. It's not the only term. It's I'm not showing what the angle is with respect to the potential fluctuations. So I don't know, and I also don't know what the density fluctuations are. And this is what makes studying turbulence so difficult. So I did not show, for example, from my data saying, you know, and you're right, I don't have the right to say, for example, in my shots, I have a higher temperature fluctuation in deuterium. I don't have the right to say that the heat flux in deuterium is certainly higher than in hydrogen. That's not necessarily the case. I have done these calculations. You can do this with a code called transp to come up with fluid-like heat diffusion and particle diffusion. So I hope this answers the question. Does it? I mean, I'm afraid I'm taking it into weird directions. So let me know if that answers your question to start with.
Well, from what I understand, when you measure the level of fluctuation of the temperature, this tells you something about the level of turbulence, but it does not necessarily tell you the diffusion coefficient. In this case, I guess the heat diffusivity or the heat flux, the perpendicular heat flux.
That's absolutely true.
Right.
I don't know.
So it's like one piece of the puzzle.
There you go. Yeah.
Yeah.
I mean, I also have, for the record, I measured with the Doppler the density fluctuation level, but not in the ion scale, on the same scales as mine, because I'm also, not only this, it's so complicated. I am just also measuring one scale of the terms because I have an antenna pattern, and I'm measuring most of the long wavelength fluctuations, which are the ones that drive most of the transport. But they could be very small scale turbulence that I cannot measure. So I'm also measuring a particular sub-sample of the temperature fluctuations. No, I was talking just before the talk with the colleague. Sorry, I forgot his name. The friend of Tobias, who was here. He works in a machine where they have a diagnostic that can measure potential fluctuations and density fluctuations called the heavy ion beam probe. But it's a very unique diagnostic, and that would be really cool to have measurements of the potential density and temperature fluctuation in the same place. Oh my gosh, that would solve the problem. That would give you a direct experimental measurement of the heat flux.
Yeah, it's here in CMAT. I'm sorry, I just wanted to chip in because we were talking with Pedro just before the start of the talk. It's here in CMAT, the heavy ion beam probe. They use it for making some measurements on for the turbulence studies in the TJ2 accelerator here in Madrid.
Yeah, well, I'm afraid that I can't offer the normal solution we have for the edge plasma, which is the ball pen probe and the Reynolds stress probe, which we have here on COMPASS. So here we can, or in the edge on COMPASS, we can measure these fluctuations and how they are correlated, but we can't stick a probe inside a plasma. So
how far in can you go?
In COMPASS, I think it's safe to go up to the separatrix. I think that since there is quite a lot of a cooperation between COMPASS and ASDEX, you probably have had the Reynolds stress probe in the past as well. I think, I hope. But yeah, that is only the edge measurements. Anyway, I wanted to ask something else as well. So you were talking about the drift wave as a source of energy and also of the ion temperature gradient instability as a source of the turbulence, the underlying instability, why it gets into motion at all. While in the edge plasma, I have been hearing more about interchange instability and so on. So I was wondering whether the kind of instability which drives your turbulence depends on the isotope effect. Like maybe there are different instabilities acting in the edge and in the core, and their growth rate depends on the ion mass.
Mm-hmm.
So do you know anything about this?
Yeah, I mean, that's what we're trying to, yeah, and I'm not allowed to show you, but with, I'm using Gene and also TGLF to look at so these are codes that solve the gyrokinetic equation, essentially. TGLF is a much lighter code, a gyro fluid code. And in that code, I've already done the comparison between hydrogen and deuterium. You're just going to have to take my word for it because I'm not allowed to show it because it's not published, and even getting this data to show you guys was complicated enough. So we can see TGLF can recover the fact that the fluctuation level is lower in the hydrogen over the deuterium. But this code over predicts, for example, the ion heat flux. It thinks it says is much larger than what we see in the experiment. And so what I want to say to you is I don't unfortunately know a lot about the conditions of the scrapable layer, and I know that the physics are different because you have you don't have magnetic field lines that are on themselves, but they touch the walls, and places like in Lausanne, I remember the machine called Torpex, which you might have heard about. They studied in detail this interchange type of turbulence, plasma turbulence of the scrapable layer. In the core, most of what the picture is that they are drift waves, and the kind of the behavior that we see in our spectra also looks like a drift wave. This is what people generally accept to be the drift wave turbulence patterns, because the turbulence is kind of rotating colloidally. So there are reasons to believe these are drift waves, but it's not one drift wave. It's a nonlinear mixing between the ITG and the TEM, usually in the core of a plasma. In the simulations that I have done, and actually I'm not showing that here, but if you look at the linear simulations that led to this slide, you would see that it's dominated by ITG, total ITG turbulence. Now, analytically, if you were to ignore all of the electron contributions and just ITG growth rate, then there may be a mass dependence there already, but I haven't, I don't know. I haven't looked into the particular equation for that, but in theory, you could find it, I think. So sorry, I can't. I don't have the ITG growth rate equation in front of me. I don't even know where to find it. Probably in the Horton paper. But it's a good question. It's a very good question. For the record, just to let you know, like we cannot measure with our diagnostic the electron heat flux, but we can infer it from transport simulations. I don't know if you know what that is. Just to let you know as an answer, because I mean, it'd be great to have the potential fluctuations, as I said before, and the density fluctuations and the cross-phase angles between them, because then that would give us a direct measurement of that. But there is a technique called transport modeling where the code, for example, transp I use, people at ASDEX sometimes use this code called Astra, which you then take the profiles from the experiment. So you go into the experiment here and you ask the Thomson guys, what's the profile over radius? You ask the volumetry guys, and you put it into a code, and you can do a power balance calculation. And the power balance calculation also gives you access to the, let me show you the output of that, if that's somewhere here, relatively fast, yes. Okay, can you hear me now? Is that okay?
Yeah, I can see it.
We got slow. So can you see this screen?
Yes.
Yeah, so this is the trans output. You can get an electron heat flux, and there's no error here. You can calculate just from the fact that energy is conserved in a very overly simplistic PDE, essentially a fluid code. So something that is probably very likely wrong. It's just that if you get the right profiles, the energy going in should be the energy going out. You make a power balance. You can calculate the heat fluxes experimentally, like pseudo-experimentally. But this is a code, so it's not as direct as a measurement. And this can be done. And I assume that perhaps you have something like transp codes in the scrapable layer as well. You can, certainly try to get something at the last close surface with transp, it would be a rough guess because it depends on your fits of the profiles. You know, here it's very hard to fit the profile.
Yeah.
But you can try this. Yeah, it's a thing to try. Transp or Astra. Yeah. Let me know if you need more information. I'm happy to help you.
Yeah, I might try and write to you in like after the lecture, because I have recently tried to see if the gyro-Bohm diffusion coefficient can be used in my SORPS ITER simulation of the H plasma. And it seems like it's not working very well. So I am trying to discuss in my PhD, like, what is actually the diffusion coefficient if the transport is not diffusive? And how do I justify choosing a particular diffusion coefficient based on experimental data?
That's an interesting question. Yeah.
That's true. I would like right now to end this official talk so we can continue this more informal and more direct discussion without the recording in the background. So at this point, I would like to thank you, Pedro, for your contribution. Thank the audience for listening and this good question discussion.